In this video, we're going to build a camera system that will smoothly follow the player as they move around the scene. We'll get started by adding a child game object to our player's prefab to act as the camera's target. The target will simply sit at the center of the player's feet, just like the pivot position of the player's sprite. We're doing this because the player's actual sprite does not move while they climb up a ledge. So we are going to move the camera's target while they are climbing to ensure that the camera follows the apparent motion of the climbing player. Then, when the animation is complete and we move the player to the top of the ledge, we will also move the camera target back to its original position. Now let's create a new script called Camera System. We will then introduce a reference to this class into our game manager because it will be managed just like the input system. We will attach the camera system to the game manager so we can use getComponent in awake to retrieve the reference, and then we'll make a call to the managed awake method. Before we go on, let's fill out the framework of the camera system. We are going to add the managed awake and late update methods, and we'll also include the onDrawGizmos Unity callback so we can eventually debug the camera's focus area. Let's also add a camera reference so we can access the camera object that is in our scene, and we'll also include a game object reference where we can store the player's camera target object. We can find the main camera game object by using its name, and then we'll retrieve the camera component from the game object. And we can find the camera target object by using the full path. We can find a child object by first referencing its parent, then using a / before adding the child's name. In this case, we're not grabbing a component, so we don't need to do anything more. Now let's introduce a new script called Focus Area. This will be a class that represents a rectangle in the scene that the camera will always try to remain focused on. This class will not be defined as a Unity component. First, we'll define a reference to the game settings object, and then we'll also need a transform reference which will hold the transform of the target game object which is currently being focused on. Presumably, in the future this could be something other than the player, but for now it's simply going to be the player's camera target transform. We are also going to set up a few properties that are based off of two rect objects. We are going to define a target rect, which will represent the player's shape. This is essentially going to be the object that the camera attempts to focus on. Then we're going to define a focus rect, which will represent an area where the target can move without causing the camera to update its position. This is so that every tiny little movement of the player doesn't cause the camera to jump around. It's much more natural in games for there to be a little bit of an area where the player can move while the camera stands still, and then only if they reach the boundary of this area does the camera start actually following. These concepts will all be much clearer once you see them in action. We will define a public auto property for the center and the size of each of these rects because they will be used by the camera system to manage its movement. Now let's define the focus area constructor. The constructor will take the target's transform as its only argument, and will store this in our private transform reference. We'll also load the settings object in the constructor. Now we'll instantiate the target rect and the focus rect. We are going to define two new settings that hold the sizes of these rects. We will call the first one camera target size and the second one focus target size. The position of the target rect will come directly from the position of the target transform, but we need to add half the height to make sure we are actually defining the center and not the pivot position, which is where our target is located for convenience. You'll see in a little while why that position makes things easier, even though we have to adjust for it right here when setting the center. Let's copy this and follow a very similar approach to instantiate the focus rect. The main difference is that we need to subtract half of the focus rect size to make sure the focus rect is centered on the target rect when we begin. Now we will define an update method that will make sure that the focus rect moves along with the target rect. We will calculate a velocity or a change in position for the focus area based on how far the target rect has gone beyond the focus rect's bounds. First, we'll update the target rect's center based on the position of the target transform. This will ensure the target rect is always centered above our player's camera target object. Then we'll check all 4 directions to see if the target rect has moved beyond the boundaries of the focus rect, and then we'll do a simple subtraction to figure out how far beyond it has moved. So if the right side of the target rect has moved 2 units past the right side of the focus rect, then we'll move the focus rect 2 units to the right to ensure that the target rect is back inside the focus rect. Finally, we will apply the velocity we calculated to the focus rect. Make sure you don't make this one long if statement because we want to be able to correct the position in both the x and y directions in case the player moved into the corner of the focus rect. Now let's go back to our camera system and add a private reference to a focus area. Then we can instantiate it in the awake method by passing in the transform of the player's target object. Then we'll call the update method we just defined in late update. We are using late update because often you want to wait until all other movement in the scene is done before trying to move the camera. Now we're going to use another smooth damp function to help make the camera's movement more natural. We're going to focus the camera on the center of the focus area, but the damping will ensure that it doesn't immediately snap to the new position. For the smooth damp, we will need to define a vector 3 that the function will use to keep track of the damped velocity, and we will also need a float that will store the smooth time we want to use for the damping function. The current value will be the transform position of the camera, the target value will be the center of the focus rect, and then we'll pass in the 2 variables we just defined. Finally, we'll move the camera to the new focus position, and we're also going to subtract 10 units in the forward direction to ensure that our camera is not right on top of the tile map, which sits at 0 on the z-axis. Now, let's draw the focus rect and the target rect using the gizmos to help us debug the camera movement. Also, all of these calculations will make a lot more sense once you are able to move around and watch exactly what is happening as the camera updates its position. Before we test this, we need to attach our camera system to the Game Manager object, and we also need to make sure to call the managed late update method for the camera system in the Game Manager. We're now ready to test this out. Your camera should now follow the player around, always keeping the player target within the focus area of the camera, and the response should have some damping so that it doesn't just snap into place. The last thing we're going to do in this video is complete our climb ledge coroutine by moving the player's target object while they climb to create the illusion that the camera is following the player's position, even though the player isn't actually moving during the climb. As you can see now, when the player climbs up the ledge, the camera suddenly jumps to their position on top because it is still following the target object. This target object jumps to the top with the player when they complete the animation. We will move the target smoothly along with the animation to ensure the camera follows. Let's start by defining a reference to the camera target object in our player's script. Then we can retrieve this reference by using the static find method that is in the transform class. This version of find only looks through the children of the current object. Once we have this reference, we can update its position in the while loop that is running throughout our climb ledge routine. To do this, we are going to use a linear interpolation function. This function takes 2 points and then returns a point between them based on a number from 0 to 1. If we provide 0, then it will return the first point, and if we provide 1, it will return the second point. But if we provide 0.5, then it will return a point that is halfway between those 2 points. We are going to use the lerp function to update the local position of the camera target object. This is quite convenient because our first interpolation point will simply be the 0 vector. This is why we set the target object to have the same position as the player. This means that the target's default local position is the origin, or the 0 vector. Then we can reuse the climb ledge offset as the destination vector because that's exactly where we want the final position of the target to end up relative to the player's original position. And the normalized animation time is exactly what we want for the interpolating value. It will be 0 when the animation first starts, and it will be 1 when the animation is complete. Finally, we will then reset the local position of the target object back to 0 when the player is moved up onto the ledge, because then we will want the camera target to be back at its original position at the feet of the player so that it tracks their current position correctly. That's all we need to do. If we run the application now, we should see that the target object moves along with the climb ledge animation. This ensures that the camera's focus area also updates its position if it needs to, creating the illusion that it is following the player's movement, even though the player isn't actually moving throughout the climb ledge action. In the next video, we will build our final state, the wall slide state. This will allow the player to enter a state where they are able to slide down a wall that they've jumped into by pressing into the wall. They will also be able to perform a wall jump action to exit this wall slide and return to the move state.